Thanks for joining me. Bevor man eine Frage beantwortet, sollte man immer seine Pfeife anzünden. Deswegen würde ich erst meine Pfeife anzünden, dann stelle ich die Frage. Ein bisschen klassisch, aber ihr müsst mich verzeihen. Ich komme aus der alten Welt. Okay, we continue in English. Apology to all my German audience. The question nobody asks about global crisis. There is a question I want you to consider before we begin. If only one country suddenly loses access to an essential resource tomorrow, how long would it take before people on the other side of the planet notice? A day, a week, a month? Perhaps the more unsettling answer is this: it depends on what the resource is connected to. We tend to imagine global crisis as a large event: a war, a financial crash, a pandemic, a natural disaster, a cyber attack, but civilization doesn't actually experience these events as isolated incidents. It experiences them through systems. A ship is delayed, a factory stops, a component becomes unavailable, a production line slows. Prices rise. Companies change their behavior. Governments respond. Consumers react. Consumers react differently as well. And suddenly, something that began thousands of kilometers may has become part of everyday life. This is the subject I want to explore. Not prophecy, not conspiracy, and not catastrophe for the sake of entertainment. Foresight, because the most useful question is not what terrible thing will happen next. The better question would be, what happens if something important stops working? And then, what depends on it? For most of human history, societies were comparatively local. Food was produced relatively close to where people lived, energy systems were smaller, communication was slow, manufacturing was geographically concentrated. A disruption could be devastating locally without necessarily becoming a global event. Modern civilization is different. Today, an ordinary product can depend on raw materials from several countries, compounds manufactured somewhere else. Software development on another continent, or electricity from a national grid, telecommunications infrastructure crossing an ocean, and financing moving through a global financial systems. This has created extraordinary efficiency. It has also created something else: dependency. And dependency is not dramatically or automatically weakens or considered weakness. The problem appears when dependencies become difficult to see, because if you don't know what your system depends on, you can't properly understand its vulnerability. So let us look underneath the surface. When you send a message across the ocean, it is tempting to imagine the information traveling invisibly through the atmosphere. Much of it doesn't. It travels through physical infrastructure. Undersea communication cables form a critical part of the world's telecommunications architecture. They carry enormous volumes of international data, financial transactions, cloud services, business communications, video, government communications, and ordinary conversations. The remarkable thing is that most people never think about them. That is precisely what makes critical infrastructure interesting. The most important infrastructure is often the infrastructure nobody notices until it stops working. Damage, faults, accidents, Natural events or deliberate interference can create rerouting, congestion, and increased dependence on remaining capacity. And here is the system lessons. The vulnerability is not simply the cable. The vulnerability is the network around the cable. Now consider something even smaller, a semiconductor. Modern economies have become dependent on extremely sophisticated semiconductor manufacturing. These components are inside computers, cars, telecommunications equipment, industrial machinery, medical devices, weapon systems, consumer electronics, artificial intelligence infrastructure, and countless products that don't look like technology at all. The semiconductor industry, extraordinary because it represents an enormous concentration of a specialized knowledge, equipment, materials, and manufacturing capability. This creates a paradox. We have made computing extraordinarily abundant, but the ability to manufacture the most advanced computing components remains highly specialized. This means that a disruption in one part of the semiconductor ecosystem can propagate far beyond the technology industry. A shortage of a component can become a manufacturing problem. A manufacturing problem can become a transportation problem. A transportation problem can become an economic problem. And an economic problem can eventually become a political problem. This is what I mean by cascading risk. The original event and the final consequence may look completely unrelated. Now let us move from something macroscopic to something enormous, the global maritime system. A huge proportion of international trade depends on ships moving through a relatively limited number of strategically important routes. Certain passages connect enormous economic regions. That creates what systems engineers would recognize immediately, a bottleneck. Imagine a highway with thousands of vehicles. Now imagine that almost all of those vehicles must eventually pass through our one narrow bridge. The bridge doesn't have to collapse completely to create a major problem. It only needs to become slower. The consequences can accumulate. Ships' weight, insurance costs change, of course. Routes become longer, fuel consumption increases, delivery schedules change, inventory strategies change as well, prices respond, and businesses begin making decisions based not on what is happening today, but on what they believe might happen next. That last point matters enormously, because markets react not only to shortages, they react to expectations of shortages. Now we reach a connection that is very easy to miss. Food production is not simply about land, seeds, and rainfall. Modern agriculture depends on industrial inputs. Among the most important are fertilizers, and fertilizer production itself is connected to energy and chemical industry. This creates a chain. Energy affects industrial production affects fertilizer availability and price, fertilizer affects agricultural economics affects planning decisions and yields, and agricultural output affects food prices. Notice the time delay. This is critical. A disruption today doesn't necessarily create a visible food consequence tomorrow. There can be a long interval between cause and effect that makes forecasting difficult. The original headline disappears, the political conversion and conversation moves on, but the consequences can still be moving through the system. This is one of the most dangerous features of complex systems. The cause can disappear from public attention before the effect arrives. Now consider the system underneath almost everything, electricity. Without reliable electricity, modern civilization rapidly becomes a different civilization. Communications, water treatment, hospitals, manufacturing, transportation, banking, data centers, food disruption and distribution, heat and cooling, data centers all depend on energy, and the dependence increasingly works in both directions. Digital systems depend on electricity, but electricity systems increasingly depend on digital control. That creates a forecasting and fascinating vulnerability. The infrastructure that manages critical infrastructure itself. So what we ask whether an electrical grid is secure, we are not simply asking whether power plants are protected. We are asking whether the entire system, generation, transmission, distribution, control, communications, maintenance, and backup, can continue functioning under stress. Again, the question is not whether failure is possible. The question is how failure propagates. Water is one of the oldest resources on Earth, but modern economies don't simply consume water for drinking. Industry needs it, agriculture needs it, energy production can need it, cities need it. Semiconductor manufacturing requires extremely high quality water, so water is simultaneously an environmental resource and an economic input, and thus produces another hidden connection. A region can experience water stress without immediately experiencing an ongoing crisis. Companies adapt, governments ration, farmers change crops, industries modify processes, but if stress continues, adaptation becomes more expensive. Eventually, the question changes from how do we use less water to which economic activities can continue here. This is no longer simply an environmental question. It is a strategic question. Now look upward. Satellites have become deeply embedded in modern civilization. Navigation, timing, weather forecasting, communications, Earth observation, scientific research, military systems, financial systems rely on extremely precise timing. Transportation relies on positioning, agriculture increasingly relies on satellite information, and governments rely on space-based observation to understand events on Earth. There is something philosophically interesting here. Civilization increasingly depends on infrastructure that exists somewhere humans cannot physically reach. A system can be critical when almost nobody can inspect it directly. And that creates a different category of risk, loss of visibility. If you can't see what is happening, your ability to respond intelligently decreases. Now put the 7 systems together: communication, semiconductors, shipping, fertilizer, electricity, water, satellites. None of these exists independently. They form a network. Electricity supports telecommunications. Telecommunications support financial markets. Semiconductors support electrical infrastructure. Shipping moves components and energy. Energy supports agriculture. Agriculture supports population. Satellite provides navigation and observation. And financial systems coordinate investment across almost all of them. This is why global risk is so difficult. A complex system can be stable for years. Then a relatively small disturbance occurs, and the system discovers a dependency that nobody had adequately measured. That is a cascading failure. The important point is that cascading failures don't require every component to fail. They require the relationships between components to become stressed. This is perhaps the most important idea in this entire discussion. People naturally look for immediate consequences. Time has to be taken into account. An event happens. They look at the market, they look at the news, they look at today's prices, and if nothing dramatic happens, they conclude that the system is resilient. but complex systems often contain delays. A shortage today can influence production months later. A production decision can affect inventory later. Inventory can affect prices later. Prices can affect investment. Investment affects capacity at a later stage. So the full consequence of an event may emerge long after the event itself. This creates what I call the visibility gap. The distance between the moment a vulnerability is created and the moment society recognizes the consequences. The larger that gap becomes, the harder foresight becomes. There is another uncomfortable lesson. Modern economies have spent decades optimizing the efficiency. Lower inventories, faster logistics, global specialization, just-in-time production, maximum utilization. These strategies can be extremely efficient under normal conditions, but resilience asks a different question. Not how cheaply can we operate, but how much stress can we absorb before the system begins to fail. Those are not always the same objective. A warehouse full of inventory can look insufficient or inefficient until supply is suddenly interrupted. A second supplier can look unnecessary until the first supplier becomes unavailable. Redundant communications can look expensive until the primary route fails. Resilience has a price, but vulnerability also has a price. The challenge for governments and companies is deciding where redundancy is worth paying for. So how would an intelligent person think about all of this? Not with panic and not with complacency. The first principle is don't look only at events, look at dependencies. Second, don't ask only what can fail, ask what depends on it. And third, look for bottlenecks and look for delays. Look for systems that appear unrelated but share a common dependency. This is where strategic foresight becomes useful. It is not about predicting tomorrow's headline, it is about understanding the structure that produces possible features. A good forecaster doesn't claim this will definitely happen. A good forecaster asks, if this happens, what becomes possible next? And then, what evidence would tell us that the scenario is beginning? That is a much more disciplined way to think about uncertainty. The world is not necessarily becoming more fragile. That would be too simple. It is becoming more interconnected. Interconnections creates extraordinary benefits, but they also create dependency. It allows knowledge, capital, energy, products, and information to move at unprecedented speed, but interconnection also means that local problems can acquire global significance. So perhaps the most important question for governments, companies, and individuals is not what is the next crisis? It would be what are we depending on that we have stopped noticing? Because hidden dependencies are where surprises live. And if we can identify them before they are tested, we have something much more valuable than prediction. We have preparedness. I want to leave you with one final thought. Civilization is not held together by one magnificent machine. It is held together by millions, perhaps billions of relationships. A cable connected to a network, a factory connected to a supplier connected to a port connected to an energy system connected to a financial system, or a farmer connected to a fertilizer, a city connected to water, or a satellite connected to a decision. The future will not be determined only by the biggest events. Sometimes it will be determined by the smallest connection we fail to understand. And that is why foresight matters. Not because we can't see the future, but because we can learn to recognize the structure that makes certain features possible. I'm Professor Dr. Mohamed Eldera, and if there is one principle I would ask you to remember from this discussion is it would be don't just watch the world for events, watch the connections between them. And I hope this has answered the question we addressed at the very beginning. And I'm really looking forward to your interactions, your questions, and make sure I'll read each and every comment and every question raised. And hopefully we will see you in the next discussion. Looking forward to them. Don't forget to drop me a comment if you have ever met me in person or learned something from me, whether in German or English. Both communities are more than welcome to participate in this community and become part of this community and to contribute with whichever, whether it's a question or an answer to a question, or your inputs are more than welcome. Thank you so much once again for joining, and I'm looking forward to see you in the next video.